Hi, in this video, we will discuss the space configuration of a complete endpoint. First, let's define what a space configuration is. It is any figure in the projective space that consists of a sub 1, 1 number of points, a sub 2, 2 number of lines, and a sub 3, 3 number of planes, such that on each of the points are a sub 1, 2 number of lines and a sub 1, 3 number of planes. And on each of the lines are a sub 2, 1 number of points and a sub 2, 3 number of planes, while on each of the planes are a sub 3, 1 number of points and a sub 3, 2 number of lines. Now the subscripts 1, 1, 2, 2, 3, 3, and so on refer to the row or column in an array. Hence, a space configuration is written as an array of this format. Now, in this array, the first column pertains to the points. The second column pertains to the lines, while the third column pertains to the planes. On the other hand, the first row pertains to each point. The second row pertains to each line, and the third row pertains to each point, rather plane. For a simple example, let's consider the space configuration of a complete 4 points. Now, this requires that no 4 points are on the same line. In other words, no 4 points are coplanar. Okay, so we have 1, 2, 3, 4. So we have 4 points. Okay, to draw a line, we have to connect 2 points, every pair of 2 points. Okay, so if we do that, we have 1, 2, 3, 4, 5, 6. Okay, 6 lines. Okay, for the number of planes, notice that the shape is a tetrahedron. So for the faces or the planes, we have the one on the right side, the one in front, the one behind, and the one at the bottom. So that is 4 planes. Okay, next, how about the number of lines on each point? So let's consider a point. How many points, okay, are on this, rather, how many lines are on this point? We have 1, 2, 3. Let's consider another point. So let's say this one. On that point, we have 1, 2, 3 lines. Therefore, there are 3 lines on each point. Okay, next, the number of planes on each point. Planes on each point. Okay, so again, we consider a point. So let's say this one. How many planes are connected to this point? Well, we have the one on the right side, the one in front, and the one at the bottom. So that's 3. Let's consider another point. So let's say this one. Okay, which planes are connected to this point? We have the one on the right side, the one behind, and the one at the bottom. So that is 3 planes on each point. For the number of points on each line, remember that we draw each line by connecting 2 points. Therefore, there are only 2 points on each line. For the number of planes on each line, okay, let's consider a line. Let's say this one. Okay, which planes or faces are connected to this line? Well, we have the one side and the one in front. Okay, so that's 2. What if we consider this line? So connected to this line are the planes at the bottom and in front. So that is 2 planes on each line. For the number of points on each plane, consider that the minimum number of points that we can use to form a plane is 3, and we have the requirement that no 4 points are coplanar. Therefore, there are only 3 points on each line. And since we have only 3 points on each line, the shape of the plane or face that we can draw is a triangle, right? So that means that we have 3 lines on each plane. Therefore, the space configuration of a complete 4 point is this one. So we have 4 points. We have 4 points. We have 6 lines. Let's write the diagonal first. Then 4 planes. Now let's consider each point. So let's complete the first row. So we have 3 lines on each point, 3 planes on each point. Let's consider the second row for each line. So we have 2 points on each line, 2 planes on each line, and finally the third row for each plane. So we have 3 points on each plane and 3 lines on each plane. As we have seen in the previous example, it is relatively easy to write the space configuration of a complete endpoint when we have only a few points. But that is not the case when we have, say, 50 or 80 points. That's why we have this general approach. So given a complete endpoint, sorry, let's ignore this S. Okay, so we have endpoints. For the number of lines, okay, we have to consider that we have this requirement that no 3 points can be collinear. Therefore, we can use only 2 points to form a line. So for the number of lines, we have to get the combination of endpoints taken 2 at a time, which is this formula, which is equal to 1/2 times n minus 1. Now for the number of planes, consider the requirement that no 4 points can be coplanar. So we can use only 3 points to form a plane. Okay, so for the number of planes, we have to get the combination of endpoints taken 3 at a time. So that is this formula, which is equal to 1/6 times n minus 1 times n minus 2. For the number of lines on each point, consider, okay, that every point can form a line with every other point. Okay, so for example, you have 4 points. If we are considering this point, then that point can form a line with all of the other 3 points. Therefore, the number of lines on each point is simply n minus 1. For the number of planes on each point, consider that every point can form a plane with every line not containing the points. For example, again, we have 4 points. So 1, 2, 3, 4. If we are considering this point, that point can form a plane with this line, right? Or with this line, or with this line. Okay, so therefore, for the number of planes on each point, we have to consider a combination of two points, but we have to deduct or to ignore the point that we are considering. So we have to get the combination of n minus 1 taken 2 at a time. That is this formula, which we can simplify to this one. Okay, now for the number of points on each line, consider again that, okay, no 3 points can be collinear. Therefore, we can use we can use only 2 points to form a line. So there are only 2 points on each line. Now for the number of planes on each line, consider that a line can form a plane with every other point that is not on the line. Okay, so yes, we have to consider every other point, but we have to deduct, okay, the 2 points that are on the line. So therefore, for the number of planes on each line, that is simply n minus 2. Okay, for the number of points on each plane, please remember that we have the requirement, okay, that no 4 points are coplanar, so we can use only 3. Okay, and for the number of lines on each plane, okay, again, since we have only 3 points on a plane, okay, then that would give us only a triangle. Therefore, we only have 3 lines on each plane. And Yes, what are constants in this list? So that would be 2 points on each line because again, no 3 points are collinear. 3 points on each plane since no 4 points are coplanar, and 3 lines on each plane. Let's consider 3 examples. First, we have the space configuration of a complete 6 points. So obviously, we have 6 points. For the number of lines, let's get the combination of 6 points taken 2 at a time. So that's 1/2 times 6 minus 1. That is equal to 15. For the number of planes, let's get a combination of 6 points taken 3 at a time. So that is 1 6 times 6 minus 1 times 6 minus 2. Though you can also use the general formula for combination. Anyway, that is equal to 20. For the lines on each point, we have n minus 1. So that's 6 minus 1. That is equal to 5. For the number of planes on each point, we have to get a combination of n minus 1 points taken 2 at a time. Well, we have this formula, and that is equal to 10. Okay, now for any complete endpoint, this one is constant. So we only have 2 points on each line. For the number of planes on each line, we have n minus 2, so that's 6 minus 2 equal to 4. The last two items are also constant for any complete 6 point, rather endpoint. Okay, so we have only 3 points on each plane, therefore we only have 3 lines on each plane. So the space configuration of a complete 6 point is this one. Again, let's write first the diagonal. So we have 6 points, 15 lines, and 20 planes. Then let's complete the first row for each point. Okay, so we have 5 lines on each point and 10 planes on each point. Okay, let's complete the second row for each line. So we have 2 points on each line and 4 planes on each line. Okay, the third row for each plane. So we have 3 points on each plane and 3 lines on each plane. Next, we have the space configuration of a complete 15 points. So obviously we have 15 points. For the number of lines, let's get the combination of 15 taken 2 at a time. So that's 1/2 times 15 minus 1. That is equal to 105. For the number of planes, we have to get the combination of 15 points taken 3 at a time. So that is 1/6 times 15 minus 1 times 15 minus 2. Again, instead of this one, you can use the general formula for combination. Anyway, this one is equal to 455. For the number of lines on each point, we have n minus 1, so that is 15 minus 1 equal to 14. For the number of planes on each point, we have to get a combination of n minus 1 points taken 2 at a time. So we have this formula, and that is equal to 91. Okay, again, this is constant for any complete endpoint. So we have 2 points on each line. For the number of planes on each line, so we have n minus 2, that is 15 minus 2 equal to 13. And again, the last two items are constant for any complete endpoints. So we only have 3 points on each line, therefore 3 lines on each plane. The complete space configuration of a complete 15 point is this one. So first we have 15 points, 105 lines, and 455 planes. Okay, let's complete the first row for each point. So we have 14 lines on each point and 91 planes on each point. Okay, let's complete the second row for each line. So we have 2 points on each line and 13 planes on each line. And the third row for each plane. So we have 3 points on each plane and 3 lines on each plane. Finally, we have the space configuration of a complete 35 points. So obviously, we have 35 points. For the number of lines, let's get the combination of n points taken 2 at a time. So that's 1/2 times 35 times 35 minus 1. That is equal to 595. For the number of planes, let's get a combination of n points taken 3 at a time. So that is 1/6 times 35 times 35 minus 1 times 35 minus 2. Or again, you can use the general formula for combination. That should give us 6,545 planes. For the number of lines on each point, so we have n minus 1. That is equal to 35 minus 1, which is equal to 34. For the number of planes on each point, we have to get a combination of n minus 1 points taken 2 at a time using this formula, which should give us 561 planes on each point. Okay, again, this is constant for any complete endpoint, so we only have 2 points on each line. For the number of planes on each line, we have n minus 2, that is equal to 35 minus 2, which is equal to 33. And again, the last two items, okay, are constant for any complete endpoints. So we only have 3 points on each plane and therefore 3 lines on each plane. The space configuration for a 35 for a complete 35 point is this one. So let's write first the diagonal. So first we have 35 points, 595 lines, and 6,545 planes. Okay, let's complete the first row for each point. So we have 34 lines on each point and 561 planes on each point. Let's complete the second row for each line. So we have 2 points on each line and 33 planes on each line. Okay, and finally, complete the third row, okay, for each plane. So we have 3 points on each plane and 3 lines on each plane. And that's it. Thank you for watching.